Hello everyone, my name is Avi Ganguly. I am from 22-26 batch of Jalpaiguri Government Engineering College and my department is Civil Engineering Department. So here I want to discuss the first part of home assignment 1 of the subject code PCC 591 or Design of RCC Structures Laboratory. I want to mention that my videos are made for our juniors, that is the future students of our college. So let's start. Here the question: given a prismatic member made of homogeneous materials having a modulus EMPA with following details: length, cross section, area, moment of inertia. Determine the axial force, translational stiffness required to be applied to achieve unit axial linear deformation. So first we discuss the types of axial forces. There are two types of axial forces, one in tension and one in compression. If we apply tension in any body, then the length of the body increases. On the other hand, if we apply compression in any body or compressive force in any body, then the length of the body will decrease. So before start discussing the solution of the problem, I want to highlight one thing, that is here the unit of Young modulus is given in MPa. MPa means Newton per mm square, but the other all values are given in meter. So for the particular problem, for this problem, we won't make the units same. That is, in here Newton per mm square, we don't make it in meter or Newton per meter square. But if we have any problem with values, that is the Young modulus is 2 into 10 to the power 5 MPa, length 1 meter, then we can do the Young modulus, we can convert the Young modulus in Newton per meter square, or we can take the length in mm. So we have to mind it to uh, check the units. We have to make it in one unit system. That is, if CGS, then all the units must be in CGS, or if we want to calculate the problem in SI units, then all the units should be in SI. But here we won't consider it. So in the solution part, we first assume the axial force required. So you all can see that let the axial force required to be applied to achieve unit axial linear deformation is P Newton. So what is the stress developed? We can easily say P by A, force by cross-sectional area. Cross-sectional area is given as A meter square. So what is the strain developed? What is strain? Strain is the slope of the stress strain curve. So Young modulus equals to stress by strain, that is sigma by epsilon. So what will be the strain? Stress by Young modulus. So here the strain is stress, that is P by A by E, P by A. So what is the deformation? Deformation equal to strain into original length. So the deformation is here strain, that is P by A into original length, that is N. Now according to the question, the linear deformation must be 1, or we have to achieve unit axial deformation. So we can write PL by A equals to 1 or P equals to AE by N. So the translational stiffness, now P is the required force. So we get our answer. So here P equals to AE by N, that is translational stiffness equals to AE by N. This is our answer. Now in the second question, a prismatic bar AB made of homogeneous material having ground modulus E MPa. Following details: length, cross section, moment of inertia is given. The LHS in A, left hand side end A is hinged and right hand side is fixed. Determine the moment, that is flexural or bending stiffness required to be applied at left hand side hinge end to achieve unit rotation. In the first problem we discussed about translational stiffness, that is the force required to provide unit axial deformation. Now we discuss flexural or bending stiffness or flexural stiffness, which is the moment that is required to achieve unit rotation. So here we assume that moment M is applied as left hand side hinge end. So we apply a moment M. So now as a reaction we can say, or if we briefly describe that if we apply a moment M at left end, then the beam undergoes a deformation, but in the B end the support is fixed. It doesn't allow any rotation. So a counter moment will develop at the fixed end to make the B end straight, or to counter the rotation at B end which is coming due to the moment M which is applied at A end. So if we apply M moment at A end, moment M by 2 will develop in the B end. Now we draw the bending moment diagram, and after that M by EI diagram. What will be the bending moment diagram? Here a rise of M, and the diagram will linearly decrease to 0 at B, and due to the moment at B, the bending moment or M by EI diagram will be negative. Here M by 2 and M by EI means M by 2 EI. The diagram is M by EI. M means the bending moment and EI, E is the Young modulus and I is the moment of inertia. So if you want to understand it, first draw the bending moment diagram, then divide each and every value of that bending moment diagram by EI. That's how you will get M by EI diagram. Okay, now we calculate summation MB equals to 0. We take one equilibrium equation, and by that we get capital M plus RA into L plus M by 2. We have to counter the moment, we have to take the moment, and at the B end the moment for the reaction developing at A end is RA into L. So by this equation we can get the value of RA, which is the reaction force at A. If B end is free, then delta B equals to half into M by EI into L into 2L by 3. This is coming from the moment area method to calculate the slope and deflection. If you don't understand this, then please refer moment area method first and then you come and watch this video. So here delta B is what? Half into M by EI into L into 2L by 3. It is the area of the moment M by EI diagram, moment by EI diagram, and this is the distance of the area from B end. 2L by 3 inch is the distance of that area from B end. And similar way for this negative part of M by I diagram. So the distance of this negative part of the M by I diagram from B end will be L by 3, and for the positive part it is 2L by 3. So from that we get delta B, that is ml square by 4I. But the B end is not free, right now. So if B end is free, then the B end will undergo this much of deflection. But the B end is not free. So the theta, if the B end is free, if B end is free, then the member will go linearly down. So what will be the theta? What will be the rotation developed at A end? That is delta B by L. So delta B by L, by doing delta B by L, we get ml by 4EI. According to this question, ml by 4EI equals to 1. We need the moment required for 1 unit rotation. So here we put theta A equals to 1. So from this we get m equals to 4EI by L. So here we can write that flexural stiffness equals to 4EI by L. Thank you for watching this video.